Now we're going to make and merge angular and linear kinematics together and convert the angular motion into its linear counterpart. This is very important, and it's the purpose of golf clubs, crank lengths, and baseball bats being of different lengths. And these differences in lengths are to enhance the ability to transfer that angular rotation into some sort of linear trajectory of the path. And that enhances the transfer of energy into the ball or the pedal in order for power production and to be a more efficient manner. This connection in general is that concept of general motion where we have that rotational component which is transferred into some sort of translational component. Remember, human motion is general, so it's a combination of both rotational and translational. Now, the connection between the angular motion or rotational motion of a body segment or a rotational structure, like the golf club or shaft, really comes down to one component, and that is radius, or how far away from the axis of rotation the point on the structure is. So during angular motion, we discussed earlier that all points go through the same angle of rotation. So they move through the same angle, but different distances or displacements relative to how they are away from it. But as we go further, we want to sit there and identify how these different angular motions, depending on how far it is away from the axis, transfers into the linear path or trajectory, the tangential velocity or acceleration of that object of interest. And so there's many aspects that we're going to talk about, but the radius is that particular point relative to the axis, and this is directly related to these linear components of motion. So when I talk to you and I ask you what is the major connection between the angular rotation and its linear counterpart, you are going to, the answer would be radius. So depending on how far away from the axis of rotation it is. So first we're going to start with the basic, and that's going to be the displacement concept. And on here, what you're going to see is you have these these are the displacement concepts here, and they're represented by S. So if we look at this diagram real quick, you have the change in angle, which is the change in theta. And you have S1 is at the radius 1, and S2 is at the radius 2. So they are different distances away. S1 has a greater radius. It is further away from the axis of rotation, which is at the elbow joint. So we talk about the displacement. First off, what we're going to talk about is we want to relate this angle. So as we go through, in this graph, you can see that the line is a straight line, right? And so that's simply the linear displacement that that point travels. But this angular path and the rotational path that the point actually travels is the arc length. And if we go further, that arc length is going to be represented by S. And so here we have the angle of motion, or the angle that the elbow joint went through range of motion. You have the different arc lengths, and then you have the radius at which it is relative to the axis of rotation. And so if we rearrange these components, you are going to see that the arc length, whatever the arc length is equal to the angle through which the joint went through range of motion times the radius. So this equation really shows you that depending on how far away from the radius, as we increase or decrease, that is a linear relationship to the arc length. So as we increase the radius, you probably guessed it, the arc length increases. As the radius decreases, so does the arc length, given excuse me, that the angle or theta, the delta, that the elbow or object went through is the same. Now, it's very important as we go forward that we talked about there's many different units that angles and angular motion can be described by, but it's very important as we go forward that you only use radians. Radians are essential because if we look at the calculation and we have degrees times meters, that's a degree meter. Not divided, but degree meter. And that is not a representation of a linear distance. or a motion, right? So we need that S1 or the S, the arc length, to be just in units of measurement of the distance. And so therefore, if we're in radians for the theta, for the angle, that is a unitless number. So if this is meters, this is unitless, arc length is going to be in meters. So we're good. Okay, so remember, whenever you do angular to linear translation, you have to keep your topic or your angular measurement units in radians. Do not use revolutions and do not use degrees. Only radians for the angular to linear translation. So now that we've identified the importance of the radius, it's in affecting linear components, we can now begin to identify the benefit of club selection and swing velocity when playing golf. Now the club head speed is what determines the linear transfer into the golf ball and its initial velocity, which, as you've seen from another lecture, affects the projectile motion of the golf ball. Now there's some other things that affect the motion, spin of the golf ball, club head, there's a couple other aspects, but what we want to do is really talk about this initial velocity and connect that into, we can then do the horizontal velocity and the V initial, right? So this component now is the longer the golf club, as we just talked about, the longer the arc length. And we'll talk about here in a second how that transfers into a greater club head velocity, which then again may lead to a greater velocity at the beginning for the golf ball. So it all comes down to, typically the golf ball is going to travel farther with a greater initial velocity. Now we know that takeoff angle affects it and height, but this one we're going to focus on is the velocity. So the first major component is going to be tangential velocity. What is tangential velocity? Well, we talked about tangential previously. And remember, tangential is where you have one point that touches the curved path. And so what this looks like is, if I take you further, all these VTs on this graph here are the velocities of tangential. And you have each of the individual R's coming out. So these are the radius. And then at a right angle, it is a tangential that identifies what the linear velocity at that point, at that impact, is going to be. And that is what we're going to talk about with this relationship of angular motion to the linear velocity. So think about tangential velocity also being the linear velocity at that point in rotation of that rigid structure. And so as we go forward, it's going to be here, what you've probably seen is much of the angular terminology and symbols are italicized. So we go back to a V, and you're actually going to see this one, V sub t, for tangential velocity. But it's that linear velocity that's tangent to the angular path. Now here, with this omega, you're going to see the angular rotation. So this is a positive angular velocity because it's going counterclockwise. And at each of these impact points with the V's, you're going to have the velocity at which it is. So depending on how fast this is spinning, you're going to have a linear or a tangential velocity at each of those points. Now, to take this further, how are we going to calculate? How does the radius come into play? Well, here's your equation. So here we have the tangential velocity, and this is a lowercase v, not a capital V, times the radius at which it is from, and the angular velocity. So if you have a different angular velocity from VT1 to VT2, then the tangential velocities will be respective of that angular velocity. So again, just like before, there's a linear relationship. If the angular velocity is the same, if I did a point here and I wanted to do VT1 sub 2, if I compared VT1 to VT1 sub 2, then the tangential velocity of VT1 is greater than the tangential velocity of VT sub 1 sub 2 because of the radius. Because they're going through the same angular rotation, the linear component is different. So again, with this concept, the major component that affects the linear translation or the tangential velocity of the golf ball, if the angular velocity is constant, is the radius. Radius from which the point is contacted. So this is why if you want to increase the linear velocity of the golf ball or the speed of the golf ball or the club head speed at impact by increasing the club length or by increasing the shaft, shaft of the pedal, or by increasing your baseball bat, then you have a better chance of increasing speed. Now, as we did before, going from position to velocity, now we have the acceleration. And with acceleration, it's a little bit more complicated because in acceleration, there are two components. There is the tangential acceleration, but there's also something called centripetal or radial acceleration. And so what these are, the difference being the tangential, again, so it's going to be the exact as before, where the concept is, it is a line that intersects at one point, the point of interest, the point of contact, the point of intersection, and it tells you the direction or the linear conversion. But there's also a centripetal acceleration, which goes directly back at 90 degrees towards the axis of rotation, okay? And we'll talk about what that is. Now, the direction of rotation here, so this is going to be the angular acceleration. And again, at this point, we have a particle that's going directly around in the counterclockwise motion. So let's break down a little further what centripetal acceleration and tangential acceleration represent relative to the acceleration resultant vector. So what we're going to have here is we're going to first start talking about centripetal acceleration. And it's really important for me to represent here that centripetal acceleration is also referred to as radial acceleration. So at some points you'll see it A sub R for radial acceleration. We don't use this because in this diagram here, it also has the resultant acceleration. We'll talk about that in the next slide. But the most important thing about the centripetal acceleration is it is directly leaning back towards the axis rotation, given the vector here. And it is representative of the radius times angular velocity squared. So the equation for this is radius times the angular velocity squared. And this is a measurement of the change in direction of the acceleration. So the acceleration completely changes direction as you go through rotation, and that is what centripetal or radial acceleration represents. So one of the important things is for rotational motion, you should always have a centripetal acceleration. If you did not have centripetal acceleration or it equaled 0, then you would have something that traveled in a straight path. So in order for there to be some sort of angular rotation, there has to be some sort of centripetal acceleration because that is a changing in the direction of the acceleration. With that said, the counterpart or the second portion of the resultant acceleration is going to be the tangential acceleration. And one thing we talked about already is this path is going to be tangential or at a right angle to the centripetal acceleration, and its component is a sub t, radius times angular acceleration. So here's where the two differ. Tangential acceleration uses the angular acceleration in its equation, and centripetal or radial acceleration use the angular velocity squared. Okay. Now tangential acceleration is going to be the magnitude of the resultant acceleration. So again, we have tangential representing the magnitude of the equation, where centripetal acceleration is the direction of the acceleration. So it is possible to have zero tangential acceleration while you still have centripetal acceleration by keeping the movement or the object in rotation. Because remember, all tangential acceleration is the change in the tangential or angular velocity, which gives you some sort of angular acceleration. Okay, but you can, if you're in angular rotation, you have to have some sort of centripetal or radial acceleration. So bringing it all together, when we talk about the linear component of acceleration, if you look back, so you have a total acceleration or linear acceleration, which is comprised of the tangential and the radial or centripetal acceleration. And these components are created through the Pythagorean theorem of how they're created. But I first want to represent what this was in the last slide, and that was a sub r. So I'm going to try to draw this a little bit better. So in the last slide, you had a sub r that was coming off to a corner in this direction, and this was a sub r. Now on the last slide, you had the centripetal was here going back, and the radial was here, or the tangential acceleration was going up. But I'm going to just transfer this. So this, we're going to keep the a sub t where it was, but I'm going to take the a sub c, and I'm just going to component up here, because again, we're just going to create another triangle, and that's what we love to do in biomechanics, is just play with our triangles and right triangles. And so now, if you can see this, remember we have calculated this, and we've calculated this, giving our two equations here, central acceleration and tangential acceleration. And to get a total, or a sub r, all we need to do now is complete the Pythagorean theorem. So if I square root and make these terms squared, because remember, a squared plus b squared equals c squared, and to get c, you have to take the square root of both sides, and that equals c. And in this instance, a sub r, which is our total acceleration, linear acceleration vector, then we need to take the square root of the square of both sides. And so your equation becomes AR equals the square root of the centripetal acceleration squared plus the tangential acceleration squared. And that is how you're going to calculate this going forward. So if I asked you the sum or the total linear acceleration, then that's what we would do. For the rest of it, you're going to simply calculate either the tangential or the centripetal. And if I say, what is the component of the linear acceleration that keeps the objects in rotation, you are going to say centripetal. If I say, what is the magnitude, or what component of linear acceleration represents the magnitude, you would say the tangential acceleration. To take it further, these are again just some more depictions of what we have and what is represented. You can see that the arrow on the inside of B, so A represents the arc length, so S equals R theta. Here we have VT, which equals R omega. And over here you have the two components, which are acceleration tangential and acceleration centripetal. Okay, and again, the centripetal is R omega squared, and the tangential is R alpha. And remember, the A here, which is this A, which you've seen as A sub R before, equals the square root of R omega squared plus R alpha squared, take that square root. So here you have each of the individual components from the angular to linear analogs created differently. And in this case, each of the motions are going counterclockwise, so they are all positive.